Okay, so we just did subset. Now we want to do intersection. So the intersection of A and B is the set of elements which are common to both. So here's A, here's B, here's what we call the universal set. Sometimes they use the U, sometimes they use this capital omega. Anyway, here's the intersection of the two sets. It's the set of elements that are common to both A and B. So as an example, we have A and B, and if we ask for the intersection of A and B with a built-in R function called intersect, we get exactly what we would expect. So all of B is in A, so the intersection is all of B. If we add NA to B and call that D, and then ask the intersection of again A with this new D, where D is this set plus NA, we still get this, so we're not getting NA, so I guess that's what we want. And suppose this is E, and in that case they both have NA, and intersection will show the NA in that case. Okay, so E has NA and D has NA, then it shows up in the intersection. But if D has NA and A does not have NA, then the NA doesn't show up. We saw that here. Okay, that's intersection. Union, we also have a built-in function for union. So again, this is union. So if we have a set A and a set B, the union is everything in either A or B or in both. So here is E, which is A and adding in NA. And here's F, which is -3 to 0. And if we ask for the union of E and F, do they have anything in common? A was what? A was 1 through 8. No, they have nothing in common. So A was 1 through 8 plus cat dog. And, and this is E. So E is A plus NA, so NA also shows up. And then also F, which is here. So they had nothing in common, so the union is just everything in E, and then also add in the elements of F. Okay, that is union. Then we have something called the complement of A. So we didn't have to build any functions ourselves for this, for intersection union. Now for this one, well, let's see, complement. Here's the set A, then the complement of A is everything outside of A, it's all the red. So that's called the complement of A, or sometimes the absolute complement of A. Okay, so it's the set of all elements in U, which are not in A, not in the white circle. So that are not in A is called the complement of A. So there's A. In the picture to the right, A is the white set. In the sets package of R, we have something called set diff. For our purposes, we can use set diff for the complement of A. So there's U, this is U. So we need to have U in order for the notion of complement to make sense, because it has to be everything outside of A and in something in U. Since it's defined in terms of U. So here is, we have a set U, suppose, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and F, which is 1, 3, 5, 7, 9. So if here's U, 1 through 10, and F is, this is like, I don't know if we covered this function yet, but 1 colon 10, we know that, we've done that many times, 1 colon 10, that's everything from 1 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is kind of a more flexible version of colon. So it allows you to go from one to something else, or from one thing to another thing, but it also allows you to define the step. So do you want to go 1 by 1, or you want to go up by 2? So here we're going up by 2, so that gives us this F. Starts at 1, jumps 2, gives us 3, jumps 2 gives 5, jumps 2 gives 7, jumps 2 gives 9, and it stops because the last possible one would be 10. Okay, so we have U and we have F. We use the colon here for U, and we used a kind of generalization of the colon called SEQ, or sequence, for F. Now we use setDiff, which is part of the sets package, and I forget now if I needed to do library sets or not, or if it's just part of R. So you might have to type in library sets before you can use this setDiff. And then we have setDiff U and F, and it gives us 2, 4, 6, 8, 10, which is what we meant by the complement of F, right? So the complement of this, if this is U, this is everything. This is the whole big set. So U is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here's F, which is in U. And the complement of F is everything in U that's not in F. So that's 2, 4, 6, 8, and 10. 2, 4, 6, 8, and 10. So we can use, we can just, since we want to call it the complement, we can just rewrite it as complement. Call it complement equals function universal and the smaller set. I just gave them that name. Universal seems obviously appropriate, and smaller, I just called it smaller. Could have called it anything, but I mean this set here. So return, and then we just use this function. So UF, but in our case it's universal smaller, and we can just test it out with universal equals U and smaller equals F. One thing I didn't mention in when we have named arguments like this, we don't actually have to put these in order. So you could have, I called this function complement, I used this function saying universal equals U, smaller equals F. I could have put this phrase to the left of this, so I could have said smaller equals F, comma, universal equals U. You can change the position of the arguments if you're using the names of them. I could have just called this function without, I didn't have to write universal equals and smaller equals. I could have just written complement U, comma, F. That would be okay, but in that case you have to put them in order. But if you use the names, you don't have to put them in order. Okay, so that is the complement of A. And this is a rule, general rule, which is always true. This says that the number of elements in A, the number of elements in A union B, so where's A union B? It's all the colors here. It's blue, the green, and the red. So the number of elements in A union B, it's everything, is equal to what? It's the number of elements in here, in the blue, plus the number of elements in B. Sorry, I made a mistake. The number of elements in A is not the blue. The number of elements in A is the blue and the green, because A is here. So it's the number of elements in A plus the number of elements in here. And what about the number of elements in B? Where's that? That's the number of elements in here. So what's that? That's the number of elements in B plus the number of elements in the intersection. So if I say n of A and n of B, I'm actually counting this twice. I'm counting it once when I say n of A, and I'm counting it once when I say n of B. So I don't want to count it twice. So I have to subtract it out once. So this is true, always true. But if A and B are disjoint means they have nothing in common, nothing in here. It means like A is over here and B is over here. They have nothing in common. In that case, then n of A union B is n of A plus n of B. We don't need this last term, but we could have this last term. It's okay because this statement is always true. But this last term, if they have nothing in common, then their intersection is 0, so it doesn't change. It's still n of A plus n of B. So this is true if they're disjoint. Okay, let's look at our code for this. So suppose we have two sets, H, which is 1 through 8, and J, which is 6 through 10. Do they have anything in common? Yes, of course they have 6 and 7 and 8 in common, 6, 7, and 8. So I think, let's see, so we can define the union of Hj equals our union function of H comma J. Now let's check the cardinality. We have cardinality, and cardinality just means the number of elements. So the cardinality of the union of Hj should satisfy this equation up here. It should be, this is n, just means cardinality. So the cardinality of A union B, that's this H union J, should be the cardinality of A plus the cardinality of B minus the cardinality of the intersection. So how do we write that? This is equals. Remember, just one equal sign doesn't mean equals, it means a sign. So this is equal. So it's supposed to equal what? The cardinality of A, cardinality of H, plus the cardinality of B, plus the cardinality of J, minus the cardinality of the intersection of H and J. We already defined the intersection in the previous slide, so this is all defined. So this side should equal this side, and when we run that, checking whether it's equal or not, we get true.